Geometry. It came from the Greek words geo and metron, meaning earth and measurement. Hence, geometry is the measurement of the earth. It is the branch of mathematics that studies shapes, positions, angles, and measurement of things. But who and for what reason was geometry created? Let's dive into its origin, shall we? Let's start with Euclidean geometry. Now, we introduce Euclid of Alexandria, the father of geometry. He was considered as the famous Greek mathematician who created the mathematical system known by many students today, the Euclidean geometry. This geometry was discussed in his textbook, The Elements, and it is the oldest geometry conceived. Prior to this, many mathematicians have discussed some concepts of Euclidean geometry, but it was Euclid who took the credit for making a comprehensive, deductive, and logical mathematical system from the results. We must take note that in geometry, there are several concepts such as points, lines, and planes that are called undefined terms. This is because no one has created an actual definition for these terms. Now, let's move on to the axiomatic system developed by Euclid. Axioms are logical and self-explanatory statements that are accepted as true. In Euclidean geometry, he stated 5 axioms. Things that are equal to the same thing are equal. If equals are added to equals, then the whole are equal. If equals are subtracted from equal, then the remainders are equal. Things that coincide with one another are equal to one another. And lastly, the whole is greater than the part. Individuals had no trouble accepting these axioms since they were all true and, as I've stated, very obvious. Accordingly, Euclid also introduced 5 postulates that governed his system. As we know, postulates are synonymous to axioms, but they are statements that can be proved. Here are the Euclidean postulates. Postulate 1. A straight line can be drawn from any point to any point. Postulate 2. A finite straight line can be produced contiguously in a straight line. Postulate 3. A circle may be drawn with any point as center and any distance as radius. Postulate 4. All right angles are equal to one another. And lastly, Postulate 5. If a transversal falls on 2 lines in such a way that the interior angle on one side of the transversal are less than 2 right angles, then the lines meet on that side on which the angles are less than 2 right angles. This postulate is also known as the parallel postulate since it characterizes what happens between 2 parallel lines. As you can see, if the numbered angles were all right angles, which are 90 degrees, then the figure will be a pair of parallel lines cut by another line. The 2 lines would not intersect as their angles are 90 degrees, hence the name parallel postulate. Frankly, the first 4 postulates were very obvious and most mathematicians during that time made no fuss about them. However, it was the infamous postulate 5 that garnered the most attention since it consisted of a complicated and long statement. Some mathematicians believed Euclid was wrong in including the last postulate, and they were saying that it was a theorem. Refreshing our minds, a theorem is a statement that may be true if proven through mathematical arguments. Since the 5th postulate became notorious among mathematicians, there were notable individuals who restated it throughout the year. First was Posidonius in 100 BC who restated the postulate as 2 lines are equidistant. Next was Proclus in the 5th century who restated it as if a line intersects one of 2 parallel lines, then it intersects the other. And lastly was Legendre in 18th century who restated the postulate as the sum of interior angles of a Euclidean triangle is 180.
While they were going through the concept, they considered what would happen logically if the 5th postulate were false. This issue has been addressed by some of mathematics' early pioneers, including Ibn al-Haytham, Omar Khayyam, Nasir al-Din al-Tusi, Giovanni Saccheri, Janos Bolyai, Carl Gauss, and Nikolai Lobachevsky. They all considered rejecting the parallel postulate, only to discover that doing so resulted in the formation of whole new alternative geometries. These geometries became known as non-Euclidean geometries, where the main difference depends on the curvature of the surface upon which the lines are constructed. But we will discuss non-Euclidean geometry in more detail later in this chapter. It was until the 19th century that John Playfair contributed Playfair's axiom, which is equivalent to Euclid's fifth postulate. Through a point P not on line L, there exists exactly one line passing through point P parallel to L. This means that any point other than point M is not parallel to point L, as even the slightest tilt can make a line touch line L. These axiomatic systems by Euclid had consequences on triangles' congruency and similarity. For recap, congruent in geometry means that a figure can be identical in form or exactly equal in terms of shapes and size. From the aforementioned postulates, Euclidean triangles would always have the total sum of their interior angles to be 180 degrees, and that two Euclidean triangles with the same size and shape are said to be congruent. Even when the forms are turned, flipped, or rotated, they remain equal. There are 5 known congruence criteria for two Euclidean triangles known as SSS, or side-side-side, wherein 3 corresponding sides are congruent; SAS, or side-angle-side, where 2 corresponding sides and the angle between them are congruent; ASA, or angle-side-angle, which means that 2 pairs of corresponding angles and the corresponding sides between them are equal; AAS, or angle-angle-side, where 2 pairs of corresponding angles and the 1 pair of corresponding sides not between the angle are equal; and lastly, HL, or hypotenuse leg, which conveys that a pair of hypotenuse and another pair of corresponding sides are equal in 2 right triangles. Now, take in mind that congruent shapes are said to be similar, but similar shapes need not to be congruent, like these shoes. This is because 2 triangles are similar if they have the same shape, which indicates that they have equal angles but can be different in sizes upon which their corresponding sides are not equal. There are 3 known similarity criteria for 2 similar triangles known as AA, or angle-angle, where 2 pairs of corresponding angles are equal; SSS, or side-side-side, which means that 3 pairs of corresponding sides are proportional; and SAS, or side-angle-side, which implies that 2 pairs of corresponding sides are proportional and the corresponding angle between them are equal. So, whenever you see a perfectly proportional triangles in buildings, infrastructures, and everyday objects, don't forget to thank Euclid.
Now, there's also non-Euclidean geometry, such as hyperbolic geometry and elliptic geometry. Hyperbolic geometry can be seen in negating the 5th postulate of Euclid, which is, if a transversal falls on 2 lines in such a way that the interior angle on one side of the transversal are less than 2 right angles, then the lines meet on that side on which the angles are less than 2 right angles. In considering a circular disc, we see that through a point P, not on a line L, there exists at least 2 lines passing through point P parallel to line L. In other words, at least 2 lines on this circular disc passing through point P do not touch line L. The sum of the interior angles of a hyperbolic triangle are less than 180 degrees as a result of this postulate. Moreover, similar triangles are congruent in hyperbolic geometry. In elliptic geometry, we can also consider the 5th postulate of Euclid. However, in this type of geometry, it is possible that through a point P not on a line L, there exists no line passing through point P parallel to line L. In visualizing this, consider a globe with the lines as great circles and the points as the points on the surface of the globe. We see that all the lines passing through point P are not parallel to line L. Moreover, the sum of the interior angles of an elliptic triangle is more than 180 degrees in elliptic geometry. Similar triangles are also congruent in this type of geometry. Furthermore, this spherical model is used in planning flight paths as well as calculating distances in air and sea navigation.
Last but not the least is we have topology. Topology is the study of properties that are preserved through deformations, twistings, and stretchings of objects. However, it cannot be cut, teared, punctured, or merged. Many questions are connected to this, such as how many holes are there in an object? Is there a space connected? What is the boundary of an object? Well, mathematicians associate the emergence of topology as a distinct field of mathematics with the 1985 publication of Analysis Situs by the Frenchman Julius Henry Poincaré. It began with the study of curves, surfaces, and other objects in the plane and 3 space. Moreover, the Latin phrase analysis situs may be translated as analysis of position and is familiar to the phrase geometria situs, meaning geometry of position. That was used in 1735 by the Swiss mathematician Leonhard Euler to describe his solution to the Königsberg Bridge problem. During the 19th century, however, 2 independent ideas emerged, resulting in the sister specialties of algebraic topology and general topology. The first was marked by attempts to comprehend the topological features of surface-like things that result from the combination of basic shapes such as polygon or polyhedra. One early contributor to the combinatorial topology, or as this subject was eventually called, was the German mathematician Johann Listing, who published the Vorstudien zur Topologie, or the 1847 Introductory Studies in Topology, which is often cited as the first print occurrence of the term topology. Another German geometers, August Mobius and Felix Klein, published works on one-sided surfaces in 1858 and 1882 respectively. Well, Mobius's example, now known as the Mobius strip, may be constructed by gluing together the ends of a long rectangular strip of paper that has been given a half twist. Surfaces containing subsets homeomorphic to the Mobius strip are called non-orientable surfaces that play an important role in the classification of two-dimensional surfaces. Klein also provided an example of a one-sided surface that is closed without any one-dimensional boundaries. This example is now called the Klein bottle, as it cannot exist in three-dimensional space without interacting itself. Well, technically, circles, triangles, and squares are topologically equivalent with each other, and this can also be distinguished by analyzing the holes present in the objects. One example of this is the alphabet topology. This topological equivalence is referred to as homeomorphism. Around 1900s, Julius Henry Poincaré formulated a measure of an object's topology. The objects of topology are often formally defined as topological spaces. As the term implies, if the two objects have the same topological properties, they are said to be homeomorphic. Although strictly speaking, properties that are not destroyed by stretching or distorting an object are really properties of isotopy. In the late 1960s, researchers worked to generalize some of the topological properties of infinite-dimensional Hilbert space. These efforts foreshadowed a new area of topology, now referred to as infinite-dimensional topology.